Hello and welcome. Today I'm going to talk about RC circuits. This is Electricity and Magnetism, videos part 9. And today's topic is the RC circuit. A DC circuit with a resistor and a capacitor and an EMF source, a battery. Let's ignore the internal resistance of the battery. It's not relevant right now. Let's connect this battery to a resistor with resistance R and a capacitor with capacitance C. This is our basic circuit. And let's put a switch here. Switch S. A two-way switch. It's either on or off. Two-way switch. Close the switch, it's on. The circuit is complete, or bring it to the off position and you have an open switch. As opposed to maybe a three-way switch. Or you can call this one-way switch. It's either on or off, or two-way switch, which would be something like this. Okay, point 1, 2, and 3. So you could move it this way or that way. So you could either have points 1 and 2 are connected, or points 1 and 3 are connected. Okay, that's what I mean by a three-way switch. If you wish, call this two-way switch, and the other one will be one-way. It's just definition. But we'll need this later. I'm going to show you why. So let's say we have a simple on-off switch and the other three in our circuit. And initially, there is no charge. Initially, the capacitor plates are neutral. Initially, no charge on the capacitor. Okay, that's when switch is open. So at t equals 0, switch is open, or it has been open and you close it at t equals 0. So you turn it on, switch is turned on. So whatever happens after t equals 0, all right? What will happen, since you have the battery as your source of charges, there will be a charge flow in this direction, a current across the resistor, and this current will fill this side of the plates with positive charges, and the other will be negative. Well, in practice, actually, in reality, it's the electrons that are moving, all right? And the other direction is what we think of the current is. The current is, by definition, the direction or the movement of the positive charges. Anyway, so when we did capacitors before, we did not even think about any current, right? You just apply the potential difference between the plates, and then you had the charge. That's still true. I mean, what we had before is this charge, Q equals to this constant called capacitance times some potential difference between the plates. But the plates do not touch each other. There's no charge flow from one plate to another, unless the plates are really close and then it's humid, the air is humid, and you have really high voltages and you're seeing sparks, okay? We're not talking about that. So where does this current come from, right? Well, we're interested in the very small time, short time, right after the switch is closed, okay? This equation is okay, but that's after you wait long enough, and that is actually a fraction of a second. It's really fast. What happens is when the first charge leaves the battery, it thinks that there's nothing to stop it. Okay, it can, I mean, the resistance, it resists, but you can still have a conducting path through the resistor. And when you reach the capacitor plate, well, the plate is large, it's wide, right? And there's room. So when that charge arrives at that plate, it can just occupy a place in some corner. Okay, here's your parallel plate capacitor with two plates, right? So this charge here arrives, okay, it's not parallel anymore, sorry. The charge arrives here, and then the other charge comes next to it, okay? The charges are starting accumulating. Of course, you will have negative charge on the other side. But the charges which still come from the battery, because there's room here, they are in motion. So we do have a current in the beginning. Until when? Until there's no more space, if you will. I mean, the capacitor has a certain capacitance. It can't hold any more charge than that. So it's when it's full, there won't be any current anymore. Okay, and then this equation will give you the total charge on the capacitor. And then, of course, you have the potential difference reaching its maximum value, right? The potential difference between, suppose you had a voltmeter between the two, right? Anyways, so that's the, that's when t goes to infinity, okay? Mathematically speaking, when t goes to infinity, in practice, it is less than a second. Then a second. You have all of the charges present in the capacitor. But what happens in between is actually what we're trying to find today. Okay, so if I would plot the charge at a given time, so this charge, I'm going to call it little q. It's a function of time now. Similarly, potential difference, I can use little v, which is also or delta v, if you will. That is the potential difference across the plates as a function of time as well. So in the beginning, there is no charge. That's what we said, right? No charge in the beginning. So this is q as a function of t. But if you wait long enough, then you will have some charge. Let's say it's this value over here. So I know that after waiting for a while, the charge will be indeed that much. Okay, I mean, a battery supplies a constant voltage, constant potential difference. If you wait long enough, you'll keep the plates at a constant potential, therefore a constant charge. And what is it anyways for our circuit here with the EMF and the resistor and the capacitance? When the capacitor is full, there's no more current. If there's no more current, which would normally flow, the charge flow is through R normally. I'm going to call it I, which is also a function of time, at least in that time frame. But that dies quickly, and when it dies, since there's no current through the resistor, the left and the right sides of the current of the resistor, the left and right sides of the resistor are at the same potential because there's no current. In order to have a change in the potential, there has to be current. When current dies off, the potential difference is the same as the battery. So the potential difference across the plates of the capacitor will be just E. Okay, so if you replace delta V by E, you get the maximum charge there. So E times C. This is your maximum charge. Maximum charge on the capacitor. So what happens right here? That's the question. In between those two extremes, when t is 0, there's no charge, and then you wait long enough, and you reach a maximum charge of E times C. What happens in between? What is the function going to look like? Q of t. What is the shape? Okay, that's what we're after. And similar analysis could be done for the current itself. So let this be the current, of course, a function of time. Now, in the beginning, remember, it's almost as if there is no capacitor in the circuit. It's just the EMF. When the switch is closed at t equals 0, it's as if those plates are touching each other pretty much, right? So there's the EMF and there's the resistance. So what current will throw, what current will be through this resistor? According to Ohm's law, E equals I. I'm going to call it I max, if you will. I max times R. Therefore, E over R. This value here is E over R. But that current, if you wait long enough, will become 0. When the capacitor is fully charged, there's no more charge flow, so the current is 0. It was this number in the beginning, E over R. So what happened in between those 2 points? This is t equals 0. Okay. I mean, Q and I are related by definition. Current is the first time derivative of the charge. So if we know how Q changes as a function of time, we can just take the derivative and find I. Okay, and that's what we're going to do exactly. Okay, so let's try to find this. Let's see what happens in this area. Okay, let's see what happens in that area. This will be called the charging phase. Charging of the capacitor. Okay, our capacitor is charging. So somewhere between t equals 0 and this infinite time, somewhere around here, we still have a current, and the charge is still not the maximum charge yet. All right, so let's write down an equation. We already know what Kirchhoff's rules are, so let's apply that. Let's apply Kirchhoff's rules. Actually, the second rule, or the first one, depending on which one you call it, the loop one, right? This is the loop, and along that loop, if you write down the potential increases and decreases, potential changes, if you complete the loop, come back to the point you start, and you write down those potential differences, they are equal to 0. The sum is equal to 0. So let's start at the switch, let's say. So it's going to be clockwise loop, so I need to go to the battery first, the EMF. And I'm going from the negative side to the positive side. I'm going from right to left. So there's going to be an increase in my potential. So that's the increase, plus EMF, E. Now I'm on the left side. I keep going. I go up. Now I'm going through the resistor. I'm traveling from left to right. And I'm going parallel with the current. The current is also from left to right. Whenever that happens, you're traveling in the same direction as the current. The potential drops. By what amount? I times R. That's Ohm's law. Just like we had Ohm's law here, we can apply Ohm's law again. Minus I, okay, I of t, if you will, it's a function of time, times R. Now I am here between the resistor and the capacitor. I'm going to enter the capacitor when I'm traveling from left to right. I'm going to go from the positively charged plate to the negatively charged plate. Going from positive to negative, there's again a decrease in the potential. And how do I find that potential? I could use this formula again, Q equals CV. It's just that it's the little q right now, but C is just a constant, so minus Q, again, it's a function of time, divided by the capacitance, and I'm back at the switch. The switch is closed, remember? So I'm back at the same point. The loop is finished. So I equate this to 0. All right? This is just using Kirchhoff's rule. Now, if I want to know how Q and I changes with time, I want to solve this equation. Okay? In this equation, let's say I'm given the EMF, the resistance, and the capacitance. Those are known, but the current and the charge are not known. Okay? It looks like I have two unknowns, but only one equation. But that's not really the case because I know that the current is the time derivative of the charge. All right? So I'm going to apply that here. I'm going to apply that here. EMF minus R times dQ by dt minus 1 over C times Q equals 0. Okay? So now the only unknown is the variable Q, but I have its derivative. Okay? This equation is called a differential equation. Differential equation of order 1. That's the order of derivative. It's the first derivative, so first. If you had d squared q over dt squared, that would be a differential equation of the second order, right? What about q here? It's q to the power 1, right? The third term is q, not q squared or sine q. Now, that would make it nonlinear if it was q squared or if it were cosine q. But if it's just q, then it is a linear equation. So this is a linear differential equation of order 1. All right, that's the equation we need to solve. So a first order and linear differential equation, DE. Differential equation. All right, okay, so let's do it. Let's solve it. I'm just gonna move, let's see, let's take that, let's divide everything by R first. Okay, E over R. So that is just dq. I'm gonna isolate this dq by dt, that's why I'm dividing by R. So 1 over RC times Q is equal to 0. And let me move that dq by dt to the other side. So I have something like this. E over R minus 1 over RC Q. Okay, so the usual strategy is just multiply both sides by dt, okay? But the problem here is I have a constant E over R. So why don't I substitute Q for something else? Or let me call this thing U. U, okay? I mean, Q is a function of time. U is also a function of time and is equal to E over R minus 1 over RC. Okay, so if that is U, then what is du? If I differentiate U, then I will have E over R is just a constant, 0 contribution, but negative 1 over RC dq. Okay, that's what I get. So I can now rewrite my differential equation. Okay, so I have here dq equals u dt, but dq is negative rc times du. Okay, let's divide both sides by u and also by negative rc. So I will have here du divided by u equals negative dt over rc. RC is just a constant, okay? It'll have a special name, by the way. It's going to be called the time constant. And you can tell right away, you have time here. Time is measured in seconds. and RC, whatever that is, should also have units of seconds. It's the dimension of time. Okay, so this thing here, RC, measured in seconds. Actually, we're going to call it the time constant, tau. The Greek letter tau stands for time constant. Or it may have different names. I'm going to call it time constant. Okay. So anyway, let's solve this. Let's solve this now, meaning integrate it, right? So if you integrate this, what do you get? So on the right-hand side, I'm integrating it from 0. Remember, this was when I started my time, from 0. And the upper limit is going to be time again, some value t. Okay, so if you don't want to have the integration, the dummy variable and the upper limit the same character, you can call it t prime if you like. I don't care. Okay, or like that. Similarly, on the left-hand side, when t is 0, what is u? Remember, u was this here. And when t was 0, there was no charge. So E over R is what you have. Okay, from E over R to that value of U. I'm just going to write U here, but you know what U means, right? U is E over R minus 1 over RCQ. So anyways, if I integrate this, du over u, that will just give me the natural logarithm. So ln u. Okay, so that's E over R minus, what is it? 1 over RC. The time constant, right? That's the time constant. 1 over RC Q. All right. And the lower limit is just E over R. That's the left-hand side. The right-hand side just gives me negative T divided by RC. So if I plug in the limits here, this will give me ln E over R minus Q over RC minus ln E over R equals to E to the power negative T over that time constant tau. All right, now when you have two logarithms subtracted, sorry, I haven't taken the, okay, sorry, I made a mistake here. I jumped ahead. It's still negative T over RC. Negative T over tau. When you have the difference of two logarithms, you can write it as the ratio. So you have here ln of E over R minus Q over RC divided by E over R negative T over tau. Now the logarithm. So E over R minus Q over RC divided by E over R will be equal to E to the power of that. If I multiply both sides by E over R, I get this. Okay, so solve this equation for Q. Solve it for Q means multiply both sides by RC first. So you will get E times C minus Q, or Q of T, if you will, equals E over R times RC, E times C, E to the power negative T over tau. Or if you isolate Q, you will get E times C and move that term to the other side. 1 minus E to the power T divided by tau. All right, so this is our formula, which will give us the charge at any time. But we know if you wait long enough, This means t goes to infinity, so the second term dies off, and then what you're left with, E times C. And that's what I said in the beginning. Remember this picture here? This value, E times C. So what happens here is just that function we just found here. So let's plot it again, all right? Let's plot it again. This is time, this is Q as a function of time. So here I have that E C as my maximum charge. Maximum charge. And this function, okay, you have an exponential decay, but the negative sign is going to go like that because it's subtracted from 1. You shift a little bit, so you get this. Okay, that is your function. Starts with 0 and reaches that maximum charge. Okay, now given this shape, you can find the time required to reach, let's say, 1/3 of that charge, or half, or 2/3, or any ratio, right? Let's say half, meaning EC over 2. What is the time that corresponds to that? Right here. This will be some special time, T1/2, if you will. Sometimes it's called, I don't know, half-time or half-life in the context of, I think, radioactivity, when you have particles, you know, going under radioactive decay. We have a population of particles which will do that, and then you wait this much time, and the number of particles left is the half of the particles, you know, some statistics. So just keep in mind there's that terminology here. So let's call it half-time, or sometimes called half-life. Just call it T1/2. But what is it? Okay, how do we find that? So we just take this value and plug it in here. EC over 2 is equal to EC times 1 minus e to the power negative t, but which t? That t we're finding, T1/2, divided by tau. Okay, so you get rid of the ECs and you have 1/2 here. 1 minus 1/2 is 1/2. Bring this term to the other side, equal to negative T1/2 divided by tau. Okay, so just take the logarithm now. ln 1/2 is equal to negative T1/2 divided by tau, right? So any number less than 1 will give you a negative number. So take this negative and then make this ln2 and then solve for T1/2, and you will get T1/2 is equal to tau, which was RC times ln2. Okay. So that is a specific time when the charge is half of the maximum charge. Using the same logic, you could find the time when you have 1/3 of the charge, okay? Just like that, ln3. All right, so that's the charge. What about the current? Let's find the current from the charge by taking the derivative. All right, so this is your charge. I is equal to dq by dt. EC 1 minus e to the power negative t over tau. Okay, the first term is a constant. Its derivative is 0. The second term has a negative in the front. and then you'll have another negative from the exponent, so it's going to be positive. All right, and its derivative is, of course, there's EC here. We're going to keep that. Now you divide it by tau. E to the negative t over tau. And tau is RC. So you have here EC over RC. C is canceled. You have E over R. So I is equal to E over R times E to the power negative t over tau. Okay, and it makes sense because when t goes to infinity, e to the negative infinity is going to be 0. But when I becomes 0, but if t is 0, then e to the 0 is 1, and you have e over r as the initial current. Indeed, that's what we said here, right? If you look at this picture here, the initial current was e over r. So that matches. Let's plot it. We're going to start right here, E over R, but it's going to simply decay like this and become 0 eventually. All right, so that's the relation between the two here. The charge increases following this function, whereas the current is decreasing, exponentially decreasing, okay? So that's when we have the capacitor charging. When the capacitor is charging, all right, what happens when we discharge the capacitor? How are we going to discharge it? Here we have the circuit. Okay, I mean, if you open the switch, you just end up with a battery not connected to anything, and then a resistor without any current through it, but then you have a capacitor with charges, and the charge cannot leave the capacitor. The charge like to be next to the other charges, right? The two plates are oppositely charged, so they stick together. How can we discharge that capacitor? We have to connect those ends again, the ends of the capacitor. So this switch is not enough to do that, so I'm going to go back to this two-way or three-way switch, however you want to call it. So let me draw again what that would look like. So you have the resistor and the capacitor, and you have the battery here. Okay, I'm going to put the switch here, but I want to add a cable here connected to the switch, this two-way switch. So when I'm charging, I want this end to meet that end, these two. But when I'm discharging, I want to cut the EMF. Okay, it's no longer in the picture, so it'll be only these two. So let's call these 1, 2, and 3. So if 1 and 2 are connected, it'll be the charging phase. Capacitor is charging, and then I have full charge. I want to discharge the capacitor. That's when I connect 2 to 3. This will be the discharging. Discharging. Okay, so here's my switch. Okay, that's free to move like this or like that. Okay, if 2 and 3 are connected, in that setting, I have now the capacitor discharging. The charges will flow in the opposite direction though. Remember, we had a current that flew. We had a current which had a direction on the resistor, for instance, from left to right. It'll be different now. Okay, so in the discharging picture, what I have is pretty much this: a resistor, a capacitor. Now these two are connected. And I have the positive charges here and the negative charges on the other side. If there will be a current here, and since current is by definition the direction of the motion of the positive charges, I expect a current from right to left on the resistor. Whereas in the beginning it was from left to right to charge the capacitor. Okay, so here's the problem though. If I just use this picture here and apply the Kirchhoff rule again, all right, I don't end up with the equation that I need. All right, there will be a sign mistake because of this changing current. That's not a good way to do it. Although some books prefer it that way, they would put an arrow in that direction, but then they would say, okay, that current is the other direction, but we're putting the arrow that way. It's confusing, okay? It's okay, maybe if you end up with the correct result, that's okay. But don't think like that. You're gonna get confused. Go back to the original equation. The one that we started with. Remember this one here? This equation here. Start with this, copy it, only get rid of the EMF. That's what we're doing. We're getting rid of the battery all of a sudden, right? So we had minus E R minus Q over C equals 0. But discharging means there's no E in the picture anymore. We get rid of that. So in the discharging phase, it is simply negative I R minus Q over C equals 0. Okay, so from the general equation, by taking E equals 0, I arrived at this. Okay, this is the equation I'm going to solve now for the discharging phase. So pretty much now we're interested in what's happening after this point, where, okay, so going back to the original picture, I'm going to try to draw them on top of each other like this. This is time. This is charge. And this is current. So we saw that the current will be changing like this. And you keep, as long as you turn the switch on, it's going to stay there. Whereas the current will remain at 0, like this. But at this instant, somebody turns the switch to here. So what will happen after that? Okay, again, if you wait long enough, and long enough means 1 second, all right? The capacitor will lose all of its charge. So you want to end up with 0 charge. And there won't be any charge flow, so you're going to also end up with 0 current. So what's happening here in between those two? Okay, so if you will, this is my new t equals 0. This is my new t equals 0. What do I mean by that? I start my stopwatch at the instant I turn the switch to 3. Okay, I mean, I can always set where I want my t0. Think like this. And everything in the past was negative, right? I mean, there's no negative time in physics, but for our purposes here, it's the part we're not interested in. But how do we fill that space now? Okay, by solving that equation. Now, that's what we're going to do. And the first thing we should do is to use the relationship between I and Q again, dq by dt. Therefore, negative R dq by dt minus Q over C is equal to 0. Same trick. Let's isolate this dq. All right. So divide by R minus 1 over RC. Q is equal to 0. Therefore, dq by dt will be equal to negative Q over RC, right? Okay, so all we have to do is to divide both sides by Q and multiply by dt. So you don't need a substitution here because there's no constant. dq over Q is equal to negative dt over RC, and integrate again from your 0 to some time, okay? Some arbitrary time in between. So the initial charge was this number here, EC, right? The initial charge was EC. Now I'm down to some charge that I don't know, Q. That happens when T is T, time is T, and the lower limit is 0. Okay, so if you evaluate this integral, you'll get natural logarithm of Q over EC, Q of T, right? It's a function of time, is equal to negative T over lower limit is 0. So T over RC, or instead of RC, you could write tau, the time constant, remember? And therefore, Q will be equal to EC e to the power negative T over tau. So this is how we connect the two here. This goes like e to the negative T over tau. Okay. Now what about the current? Let's make room for current. What do? I take the derivative. That's all I do. So the current is then the time derivative of the charge. See, I have a negative here, right? Negative in the exponent. So this will be negative EC divided by tau times e to the negative T over tau, and tau is RC. So I is negative E over R, right? C's cancel. Tau is RC. So EC over tau is E over R times e to the negative tau. So both the charge and the current are both exponential decays, but the charge is positive and current is negative, which is you expect, right? I mean, take the derivative, find the slope of this decay at any time, you'll find a negative number, right? So there has to be a negative current there, but it has to go to 0 again. So this value here is equal to negative E over R, just like this was E over R. Okay, so that's how the current changes. As soon as you do that switch, if you switch that from 1 to 3, the direction of the current becomes negative. So it jumps to that value. It starts from maximum and goes to minimum. Okay, you may say, okay, how does it happen? I mean, in physics, do we have these things jumping up and down like that? I mean, don't we need continuous curves? Well, in a way, yes. But the math we are doing here, based on the principles we're applying, you know, we just get this result. So we just patch these, okay, copy and paste. So if you could zoom in there, the physical application, and if you were able to solve the differential equation for that problem, particular setting, and I don't even know what they could be, okay? I'm just speculating here. Maybe you would see some, maybe a spike, or maybe, you know, I mean, I've seen those spikes in an oscilloscope before, but maybe you would see, if you could zoom enough, you could see some other effects there. But we're not interested in that right now, okay? This is actually the solution here, like you see. So this is the discharging phase. And these are the formulas for charge and current. All right. Okay, so what about energy? All right. Now, in an RC circuit, we have 3 components: the battery, the resistor, and the capacitor. Capacitor is used to store charges, and storing charges means creating an electric field between the plates. And if you remember our discussion regarding energy density associated with an electric field, we had this. Okay, the electric field is there, so this applies to actually any electric field in a space, in a given area or space, volume, let's say. You don't even have to have a capacitor. Whenever electric fields are present, you have energy there. But this way, we're storing energy in the capacitor. Okay, storing energy in the capacitor. Energy stored in capacitor. Even when you turn the switch off, or when you have current died off, you know, you will still have energy. It's in the capacitor. That's why they put warning signs in, you know, all the radios and maybe other equipment where they use big capacitors. Okay, they say, even if you unplug it from the power, do not try to open it. Okay, take it to a service repair professional. And why? You may get shocked. Okay, I mean, that's because there's energy stored there. If you short it with your finger, you know, you may feel a shock. All right, capacitor discharge. Anyway, so there's energy there. What about the resistor? What's happening there? Well, we also saw that before. By the way, when, let's say, when the capacitor is full, we know that we can write the energy or energy per time, which is power, of course, right? Power. For a capacitor, we could write it as Q squared over 2C, or 1/2 C delta V squared, or in terms of Q and V only, 1/2 Q delta V. I mean, we saw this before. And when the capacitor is full, you will have maximum energy. Well, we want to find what happens until we get there also. So I'm not going to use these formulas directly, but let's keep that in mind, okay? You guys know this from before. What about the resistor? Now, resistor actually has something to do with energy only when there is a current through it. Okay, if the current is zero, there won't be any energy dissipation on it. So when you have current, I, all right, energy will be dissipated. Dissipated at a rate, which is by definition power, equal to I squared times R. Okay, I squared times R. And these two components are connected to the charge source or the charge pump or EMF, as you call it, electromotive force, which is the battery here. So that's your power supply. Okay, so the power supplied by the EMF. And you can write it as I times E. Okay, so these three should conserve the energy. So it's like you're getting money from your ATM, from your bank. Okay, get the money. That's your power bank. That's your EMF, and then you spend some of it in the mall. That's your I squared R, and whatever is left, you either put back in your wallet or put it into a different account. Okay, so you save it somewhere. That's like the capacitor. But of course, the sum of your expenditure and your savings, if you add them up, that's what you originally got from your bank, if you will. Okay, so there's an energy conservation here. And you can see it like this too. Where's our equation? This one here, okay? E minus IR minus Q over C. Now think about it. Think about writing it again. Let's write it in this form though. We have E, potential increase, and then we have potential decrease by the amount IR. And then going from the positive side to the negative side, there is some decrease in the potential, delta V, and then we end up with zero. This is the potential rise and fall, add up to zero. But we know that the charge, the capacitor, is proportional to the potential difference, delta V, which is also a function of time. But if I solve for delta V, I get Q over C, right? Q over T. So E minus IR minus Q over C equals zero. Now multiply this by I. Multiply both sides by the current. So you will get IE. Okay, and then move these terms to the other side. I squared R plus IQ over C. Okay, so this is not the energy, but the power, of course. So the left-hand side has to do with the battery, power supplied by the battery. The first term on the right-hand side, this is the resistor, the power dissipated at the resistor. And now this is the rate energy stored in the capacitor. Okay, and this is happening between t equals 0 and t equals infinity. In between, we have this change. No matter what the values of Q and I are, they change the way that we just found. No matter what the values are, if you add the energy rate at the resistor and capacitor, you get the power from the battery. Okay, so this is what I'm talking about. So I is, let's say we're charging, okay? We're in the charging phase. So I as a function of time E over R times e to the power negative t over RC, okay? And the charge is equal to EC 1 minus e to the power t over RC. So we could check this, meaning we could plug these into the equation there. Okay, and the left-hand side should match the right-hand side. We could do that. We could also integrate that, because power is energy per unit time, or the rate of energy per time. If you integrate that, you get energy, right? So also try, after plugging in, try integrating. So what letter did we use for energy? U. du by dt in a way is power. So to find energy, you could just integrate power. All right, so let's try all of that. Excuse me. So on the left-hand side, I need I multiplied by E. E is a constant, right? So E times E squared over R times e to the power negative t over RC. That's equal to I squared. That is E squared over R squared multiplied by R. So we have E squared over R. And then I'm going to square the exponent here. So exponential negative 2t over RC. Okay, and then plus, now I times Q. These are going to be multiplied and divided by C. So I'm going to have E over R times E times C divided by C. I will have E squared over R again. So this times that, I have e to the negative t over RC minus e to the power negative t, negative 2t over RC. All right, I mean, you can tell actually this will give you the same thing on the right and left. 0 will be equal to 0. Why? Because you have negative t here. So let me mark those with the same color here. This term will take care of this term here. And then with blue, e to the negative 2 term will take care of this. So it checks, okay? I mean, we just show that, we just see that the expressions for I and Q are not in contradiction with this energy argument. I mean, pretty much we started with that equation to get that result anyway, so no problem there. It's just a confirmation. But what I want to do is the integration part, because I'm going to integrate these terms now to find the power. So for the battery, for the EMF, here's the integral I'm considering now. The thing on the left-hand side, right? I'm integrating E squared over R times e to the negative t divided by RC. I'm going to integrate this from 0. That's when I turn on the switch and start charging up to some arbitrary time t. This is my upper limit. Okay, I'm integrating like that. So this will give me negative, right? E squared over R times RC e to the power negative t over RC. Limits are from 0 to t. Okay, e to the 0, the negative term, the second term is 1. E to the 0 is 1. That's minus. There's another minus here. So let's get rid of that minus sign. And this r cancels as well. So we get e squared c 1, okay? That's e to the 0 term, 1, minus the upper limit, e to the power negative t over RC. Okay, so this is the energy you get from the battery. You lose that much, exactly that much energy from the battery. Let's keep going. What about the energy dissipated in the resistor? For the resistor. Now I need to integrate this term here, 0 to t, e squared over r, e to the power negative 2t divided by RC, right? dt. So again, this is negative e squared over r times RC, right? And then e to the negative 2t over RC. Now forget a 2 here, so RC over 2. All right, so if you plug in the limits, here's what you get. R's cancel. E squared times C divided by 2. 1 minus, I'm just getting rid of the negative here with the minus of the other one. So positive 1 minus e to the power negative 2t divided by RC. Okay, so if you wait long enough, means t goes to infinity, the second term will be 0. So when you wait long enough, means t goes to infinity, practically a second is more than enough. But when it happens, e to the negative infinity goes to 0. Therefore, the energy is e squared c over 2. You can use the same argument for the battery if you wait long enough, right? This is the energy you get, e squared c, which is twice this amount, okay? So the energy that dissipates in the resistor, if you wait long enough, means capacitor is fully charged. That will give you only half of the energy, all right? So half of the energy you get from the battery is just used to heat up the resistor, which leaves the other half. The second half would be stored in the capacitor. That's what it means. So for the capacitor, I'm going to do my integration again and find an expression. But I know that if I take that t to infinity for that expression, I will get e squared c over 2. I have to. That's what is left from the original energy. So 0 to t. Now I'm integrating what? This term here, e squared over r, e to the negative t over RC minus e to the power negative 2t over RC. All right, so you can take that integral. Let's do it to find the energy stored in the capacitor. This is just like we did before, negative e squared over r times RC e to the negative t over RC. And then there's a negative here. This is also negative, makes positive. E squared over R times RC over 2. E to the power negative 2t divided by RC. Okay, so get rid of the R's. All right, and then that's your energy. Oh, limits. Let's plug in the limits. 0 to t. So you will have here negative E squared C e to the negative t over RC minus 1 plus E squared C over 2 e to the power negative 2t's over RC minus 1. Okay, so you can even simplify more. You could factor this E squared C business and get rid of the negative. If you just want to make it look similar to the other guy here, so you could make it E squared C divided by 2. Okay, so you would have minus E squared C over 2 here, and then plus E squared C over there. That gives me 1/2 E squared C, which is okay. I have 1 here. And then I have E to the negative T over RC term. I have 1 over that. There's 1/2, so I need to put 2 here. And I need the negative sign in the front. And then I need now E to the negative 2t RC term. And it has to have 1/2, which is here. And it's a plus. Okay, so that is my energy there. So let's look at the summary now. We have, let's use the red. This is the energy you get from the battery. This is the energy dissipated in the resistor. And here's the energy stored in the capacitor. Okay, check that limit. When t goes to infinity, e to the negative infinity terms will go to 0. So this is 0, that is 0. What you're left with is equal to E squared C over 2. Okay, like 1/2 CV squared, remember? That's what it is. Okay, so let's plot these now. Let's plot these on the same graph. So we have the time axis and here energy. Okay, whether it is the energy stored in the capacitor or dissipated in the resistor or the energy get from the battery. Let's start with the battery. We know what maximum value should the battery have, which is E squared C. Okay, it's right here. The first formula, right? E squared C. So we know how to draw that function. It's just this. Right? That's the battery. Okay, what about the resistor? The resistor is right there. It looks very similar to the battery, so we know how to draw this as well. Let's use green. We just know that when t goes to infinity, it's going to become half of E squared C. So the half is right here. E squared C over 2, right? So we know the asymptotically, is that the right word? When t goes to infinity, we have to reach that. So it kind of looks like this. This is the resistor. Okay, and then the final is the capacitor. Let's use red. This function here. So you could plot these in a computer, right? MATLAB, Mathematica, or whatever your favorite software is. But we know that this function, when added to the green line, the resistor, should give me the blue line. Okay, so if you do that, and you know that when t goes to infinity, you have to reach this e squared c over 2 again. You want to end up here. You want to start at 0, you want to end up there. And it looks very similar. Probably my drawing doesn't look like the computer, but it's going to look like this. Okay, it's going to go increase like this, and then quickly turn, and then come like that. Okay, so that is the energy stored in the capacitor. All right, so that's the RC circuits in a nutshell. But of course, the possibilities are almost endless that things you can do with these R resistors and series and capacitors. Later, when we do magnetic fields, we're going to add the coils to this. LRC circuits, if you will. So you can do lots of things with these basic circuit elements. Okay, but that's the RC circuits in a nutshell. I'm going to stop here. In the next video, we're going to start magnetic fields. Okay? All right. So till next time, goodbye.